Today we are going to start a new chapter, Introduction to Inference. And in this chapter we are going to discuss two major topics. The first one is estimating with confidence, and the second one is tests of significance. And we are going to briefly mention the third one and the fourth one, but we don't discuss the much more details. So far we already know the survey or the experiment we studied so far is only applied to a sample. But the conclusion we obtained, we want to apply to the population. So any method for drawing conclusions about population from sample data is called statistical inference. Basically, we have two methods. The first one is called confidence intervals. In confidence interval, we estimate a value of population parameter, a range of values with associated confidence level C. C means confidence level. For example, we used these examples before for many times. If we want to know the mean USM student GPA, and as we said, we do not want to calculate the GPA for all the student body, which is the population. Instead, we randomly, by following some rules, choose a simple random sample, and we calculate the mean GPA of that sample, and we try to get a conclusion about the population mean GPA. And if we state the result of our estimation as, for example, the GPA is between 2.5 and 3.5 at 80% confidence level, that gives us an interval. The interval is from 2.5 to 3.5, and 80% here is the confidence level C. And we can see we are 80% confident that the mean USM GPA is between 2.5 and 3.5. So that is the first method to infer the population parameter. The second method is called test of significance. It assesses evidence for a claim about population. In our class, we are going to discuss usually the mean of the population. And the significance level is the largest p-value tolerated for rejecting a true null hypothesis. And we are going to, in this chapter, we are going to discuss hypothesis, null hypothesis, and rejecting a null hypothesis, and also the concept of p-value. Again, in this our example, we can claim that we reject the hypothesis that the mean USM student GPA is 2.5. So what's the meaning of this? We are going to discuss in this chapter. Inference is appropriate when data are produced by either a random sample or a randomized experiment. We have all the techniques that to design a randomized experiment and or to take a random simple sample. As we already know, first line, we need to choose a random sample. Suppose we already have a random sample, then we can calculate or find out the mean. We use a X bar to represent. This is the mean of the sample. And it is a unique number for any particular sample. For example, for this class, this is x bar, and we said this is x1 bar. X1 bar for the first class, for the first sample, that is unique. So this is the only one. We cannot have the second one. But if you choose a second sample, for example, I choose another class, another sample, and we also discuss the mean GPA of that sample, but that is for the second sample, so we are going to get x2 bar. And we can do this, the same thing for x3 bar and so on, we get a lot. And we have every reason to assume that all these xi's, x1, x2, x3, all these bars, these means of the sample are different. The possibility for them to be equal is equal to 0 if they are continuous. In fact, there are many different values for the sample mean, and virtually none of them would actually be equal. None of them would be actually equal. That means the probability for them, for any two to be equal, is actually equal to 0. And also, none of them will be equal to the true population mean, mu. Here, this x bar means the mean for the sample. The mu means the mean for the population. All this x1 bar will not be equal to x2 bar, is not equal to this, and we are not equal to the population mu. The probability for them to be equal is equal to 0. So how can we make the conclusion to the population mu if we actually all these means will not be equal? And we already know from last chapter we discussed the sample distribution. Actually we have good news, because the sampling distribution is narrower than population distribution by a factor for square root of n. In this example here, suppose this is the here, this is the population distribution. It's normal distribution, and the standard deviation here equals 7. And if we choose a sample size equal to, in this example, equals 10, then the sampling distribution also satisfies a normal distribution. Both normal distributions have the same center here, but the sampling distribution have a smaller spread by a factor for square root of n. Square root of n here equals 3 point something, so it's 3.16 times smaller than this one. That means if we use a value from the population, for example from here, to approximate the mean of the population, it will be not that accurate. Instead, if we use a mean of any sample from here, this sample, for example, this value or this value, this one will be much more accurate than we use the mean, any number from the population. So that is the beauty of a sampling distribution. Therefore, the estimate gained from our samples are always relatively close to the population parameter mu. Next topic, we discuss how to obtain population parameter from samples statistics. We need to consider several questions. The first one is the number of samples. Do we need multiple samples? Or we can just use one? We can use this one, for example, one class, the mean of this class to represent the USM mean GPA. Or we need to use two classes, or we need to use three classes, or we need more random samples. So that is the first question. We know if we have more, then it may be better. The second one, how about if we have only one sample? Then what will happen? Can we still get a relatively accurate estimation? We need to consider these two questions. The type of approximation, and we have basically also two types. The first one is called point. It's point. The point estimate are the single most likely value of a parameter. For example, I ask, what is your score of your midterm test? I said, okay, I get 90. That is a point estimate. It is the single most likely value of a parameter. For example, the point estimate of population mean, the parameter is the sample mean. So this one. What is the mean GPA of the USM student? It's 3.0. How you get this? Okay, because a random sample, which is our class, the mean of the sample equals 3.0. So I just use that one to represent the mean of the population. So that is called point estimate. The second method is confidence interval. From this sample, and we get a range called intervals. Intervals are a range of values likely to contain the population parameter. Next, we discuss the essence of statistical inference. And I believe this is the most important concept. This is the most important slide in this chapter. This is the foundation for statistical inference. So everybody should understand this without any problem. First line, the first point, we already know that. If we know the population parameter, the population parameter mu, if we know this, then, and we take a random sample first, and the size equals n, and we get the mean of that sample, and we said we get this x1 bar. Then we take the second random sample, and we get x2 bar, and we get a lot, and we draw that, we get a density curve of x bar. X bar means the mean of the samples. X bar, x1 bar, x2 bar, all this. And we know the mean of this sampling distribution is equal to the population mean. What we have is we said the mean of the population bar, the mean of the sampling distribution equals the population mean. We know this from last chapter. So it is here. Now, for x1 bar, x2 bar, all this sampling the mean of the samples, it will have a normal distribution, mu here, and the standard deviation will be equal to the population standard deviation divided by the square root of n, which is the sample size. N is the sample size. From the second chapter, we know for one standard deviation, plus one standard deviation, and minus one standard deviation, within this range, we are going to have about 68% of proportions or probabilities. And for plus and minus 2 standard deviation, here, this is minus 2, this is plus 2. For this one here, we are going to have 95.4, okay? Approximately equals 95% proportions in the first chapter or probabilities in the last chapter. So this is area equals 0.95. Because this is a sampling distribution, so this standard deviation should be sigma over square root of n. That means at this point, that is 2 sigma over square root of n. We cannot ignore this square root of n because this is the sampling distribution. And this one is negative 2 sigma, which is the population standard deviation divided by the square root of n, and this sigma over square root of n gives us the standard deviation of the sampling distribution, and plus 2 minus 2, because this refers to the sampling distribution. And if we choose the first sample, and we said the mean of the first sample equals x1 bar, the mean may be at this point. Suppose I said the first mean is here, and for the second one it may be here, and the next one is here, next one is here, next one is here, and all this red dot will be the mean of the samples. From the chapter 1, the properties of normal distribution, we know that 95% of this red dot, which are the means of the samples, will be within mu plus and minus 2 standard deviation of the distribution, which is plus minus 2 sigma over square root of n. So you can see here we have we draw this, we have 20 samples for illustration purpose. So only this one is outside of plus and minus with this range. So outside this range. So only this one outside this plus and minus square root for plus and minus standard deviation. And all other 19s will be within this. So 19 divided by 20 equals 95%. This is the only one which is 5%. So this is for illustration purpose only. And we already know this. We combine the first chapter and the last chapter. So this is not new. We just combine the concept from these two chapters, so we should understand this without any problem. Now, as we said, we already know this x1 bar, x2 bar, x3 bar, all this from our experiment. But we don't know the population mean. We don't know this. Because we want to, this is the population mean. We want to infer that from the samples. Suppose we get only one, for example this one. We get this is the only one, this is x20 bar, for example this one, or any one, x1 bar. Once we can get this, x1 bar. Once we get this x1 bar only, suppose we have only one sample, how to infer this mu? So that is the question of the inference, or this is actually the essence of the statistical inference. So let me repeat. We know this x1 bar, which is the mean of the sample, random sample. How to infer the population mean mu here? We don't know this, but we want to know this. What conclusion can we get regarding the population mean mu? Right? We still try to use the fact that we already discussed in the first point. Let's see this way. Once I get the first one, I know this one possibly be within this plus minus 2 standard deviation. And if we get to the second one, this one may also possibly within mu plus and minus 2 standard deviation. If we do a lot here, then 95% of this sample means will be within mu plus minus 2 standard deviation. Because the distance are symmetrical, the distance from me to you is the same as the distance from you to me. The distance from this mu to this x1 bar is the same as the distance from x1 bar to mu. So if this x1 bar, so here is the key. If x1 bar is within, I said close, for example, close to mu, here I mean within 2 plus or minus 2 standard deviation within this range, then the mu will be also within. So if x1 bar is within plus minus 2 standard deviation with of mu, then mu is also within plus minus 2 standard deviation of x1 bar. The distance from here to here is from a distance from x1 bar to the mu equals the distance from mu to the x1 bar. We already know this from that point. Then this is our inference. So let me repeat this. We have only one sample, which is the first one. And we calculate the mean for this one, we get this. How do we know about the population mean? Mu. Our conclusion is mu will possibly within plus and minus 2 standard deviation of this x1 bar. Because that is plus or minus 2, that gives us 95%. So we said parameter mu must be within roughly 2 standard deviation from the sample average x bar in 95% of all samples. If we get this one, x1 bar, x2 bar, all these bars, we don't know where is the mu, but we can conclude that mu will be within this range of all 95% of the samples. 95% is because of this plus or minus 2. If we use plus or minus 1, then this 95% will be 68%. If we use a plus or minus 3 sigma over square root n, then that will be equal to 99.7%. But most generally we are going to use 95% here. Okay, so this is the essence of statistical inference. We understand this theory. Next time we are going to use an example to show how to understand this further. The weight of a single egg of a brown variety is normally a normal distributed with the mean equals 65 grams and the standard deviation equals 5 grams. 5 grams, this one is the mean of the population. This is the standard deviation of the population. So this, because it's population. Now, we take a random sample from this population and put them in a carton, one carton, and the sample size equals 12. So we put these 12 eggs in one carton. So that one carton of 12 brown eggs is random sample of size 12 from the population. And the population satisfy normal, the mean equals 65, which is mu, and the standard deviation of the population equals 5. So I want to make sure everybody understands this. This is mu equals 65, this sigma equals 5. Because this carton of egg is a sample, so it will follow the sampling distribution. The sampling distribution of a normal distributed population is also a normal distribution. And it satisfies this n mu, because we said before it's a mu x bar will be equals to mu. So this is mu x bar will be equals to this mu. So here, that is this one. And this sigma of x bar will be equals to sigma over square root of n. So this sigma x bar equals this sigma over square root of n, and n equals 12. So from here, and we just change here. We plug into numbers, so this mu equals 65, and sigma equals 5, square root of n equals square root of 12, and this gives us 65, and this one is 1.44 grams. So this is the mean of the sampling distribution, and this is the standard deviation of the sampling distribution. Now, suppose we have a lot of cartons. We have a lot of random samples with size, the same size 12. And this 95% of all these cartons, the sample mean will be within roughly plus or minus 2 standard deviation over square root of n of x bar. X bar is the mean of that sample from the mean. That means 65 plus or minus 1.44 times 2 so equals 2.88. And again, this one is explanation of the first point. Then next, we are going to explain the second point. We buy a carton of 12 eggs, white eggs instead, the size n equals 12. We measure the box, it is equals to 770 grams. So we can easily calculate the mean for this sample. So x bar of this sample, because we have only one sample, we can write x1, or we can just use x bar. That means this is the mean of this sample. Will be equal to 770 divided by 12. The total equals 770, and the size, there are 12 eggs inside. So divide by 12. So the mean of this box, or the mean of this sample, equals 64.2, which is listed here. So x bar equals this. Right. X bar equals 64.2. We have only this piece of information from the sample. We know the mean of the sample equals 64.2. We know another piece of information, which is the standard deviation of the egg of the population. This one equals 5g. So this one equals sigma. Sigma equals 5. Sigma equals 5. And this sigma is the standard deviation of the population, not the standard deviation of the sampling distribution. Make sure this sigma is the population standard deviation. So we know only two things. The first one is the mean of the sample, or in this example is the cart, the carton of the eggs equals 64.2. And the population standard deviation equals 5. Now what we want is what is the mean of the white egg population? If we want to use a point estimate, then you are going to claim the mean of the white egg population equals x bar, so equals 64.2. that's it. So that's the first method. The mean of the population is estimated with the mean of the sample. In this example, we have only one sample, so x bar, which equals 64.2 grams. We don't need to care about the standard deviation because there's only one sample. So that is the that is called point estimate. That's the first one. But we don't use this method in this class. In this class, we are going to use confidence intervals. So we need to give it an interval. The interval is 64.2, which is the x bar, because which is the x bar, because we know this. And plus minus, and we use 2 standard deviation. This standard deviation is the mean standard deviation, and divided by the square root of the size n, which equals 12 in this example, and this part equals 2.88, and this one, we know this here equals 64.2. So our conclusion is the population mean of the white eggs is given by a confidence interval. It is 64.2 plus and minus 2.88 grams. Because of we use 2 here, so that gives us a confidence level of 95. So our complete conclusion is we are 95% confident. 95% is because of these 2. That the population mean mu here equals is between this one minus 2.88 to this one plus 2.88. So all roughly within this plus and minus 2 standard deviation over square root of n of the x bar. So this is how we infer the population parameter. We already know the confidence intervals are ranges of values with an associated confidence level. We mentioned a lot of times confidence level. In our previous example, it said 95% confident. We are 95% confident. Confidence intervals for means are intervals constructed using a procedure that will contain the population mean specified proportion confidence, this is C, of all the time. If we do a lot of samples and C proportion of all the samples of the sample means will contain the population mean. Now look at this example. And we have population here. I don't know what we are talking about here, what we are measuring here. But anyway, we have some result. Maybe maybe 272, 278, maybe I don't know, maybe score or something, or maybe. Okay, anyway, that's not important. Right? Suppose we have a population here, and we don't know the mean of the population. We don't know this, but we do know the standard deviation. Right? That is key in this chapter. In the next chapter, we are going to discuss if we don't even know the standard population of the population, how are we going to estimate the population parameter. In this chapter, we don't know the mean, but we know the standard deviation. It's easier. What we do is we choose a random sample, simple random sample of size n equals 840. and we measure that the mean for that one equals 272. And the mean for that sample equals 272. So this one equals x1 bar. Then we need to give an interval plus minus. We are talking about 95% confidence. So 95% means this one equals 2 here. Then the standard deviation equals 60. So that's 60 here. Then divided by the square root of size. So 840. And this gives us, this part gives us 4.2. So this is this part, 4.2. So from the first sample, if we have only one sample, then we conclude that the mu, the population parameter, the population mean, is within this range, which is 272 plus minus 4.2. Right? So that is the inference process. How about if we take another random sample, the second one, of the same size, n equals still equals 840, but that is the second. This is the second sample, and we calculate the mean of that sample. As we said, each mean of the sample will be unique. They have 0 probability to be equal. Okay, in this example, that's mean equals 268. It's not equal to 272. Then, if we know this only, how to infer the population mean? We still use this one, x2 bar plus minus 2 standard deviation over square root of n. And we can see for this sample and this sample, the second part is the same. 260 over square root of n. This n is the sample size because these two are the same size. And 60 refer to the population standard deviation. These two samples are from the same population, so this sigma is the same. And this 2 is from the confidence level, because we are talking about with the same confidence level. So this 2 must be the same for all these estimations. So from here, we assume the mu equals 268 plus minus 4.2. If we take the third simple random sample, right, then we can conclude that mu equals the mean of this sample, which equals 273, then plus minus the same number, 4.2. Then how to understand this? We're confident at 95%. Or we said we are 95% confident. How to understand this? If we have many these samples, 1, 2, 3, 4, 5, a lot. Okay, 95% of these intervals, this one, second interval, third interval, 95% of all these intervals will contain the real mu. This one is yes or no, this one maybe no. This one yes or no, maybe yes, maybe no. But 95% of all these intervals will contain the real population mean. So that is the meaning for this 95% confidence. Looks like if we want to estimate the population mean, we need to form the sampling distribution. So that means we need to have a lot of samples. So actually, we do not need to take a lot of random samples to rebuild the sampling distribution. So that is not, we don't need to have the sampling distribution. If luckily we have this sampling distribution, then we know the mean of the sampling distribution equals the population mean. So we do not need to estimate We just calculate that it will be exact. So there's no estimation involved if we know the sampling distribution. The key here is we don't know the sampling distribution because we have only one sample. We cannot compute the mean of the sampling distribution because we don't have it. So we can only estimate the population mean with only one simple random sample, with only one. And we need to know the size of the simple random sample and also the standard deviation of the population. Standard deviation of the population. Then we can estimate or we can infer the population mean, which equals the mean of your sample, the only sample, then plus minus with some standard deviation of the sampling distribution, although we do not know the sampling distribution, but we know the standard deviation of the sampling distribution. Then with some constant here related to or depends on the confidence level. If we want to 95% confident, then this one will be equal to 2. The foundation for this estimation is because the sampling distribution is narrower than the population normal distribution. So we are going to have a better estimation of the population mean from the sampling distribution. Okay, now we review a little bit because this picture, this diagram picture is so important that we want to emphasize this one more time. With 95% confidence, we can see that the population mean should be within roughly 2, as we mentioned several times. This 2 is depend on 95%. If we change this 95% to other numbers, this 2 will be changed. So in this example, 95% confidence, then it will be roughly 2 standard deviation. The standard deviation, keep in mind here, is the standard deviation of the sampling distribution. This is the standard deviation of the sampling distribution, not the standard deviation of the population. The standard deviation of the population is sigma. The standard deviation of the sampling distribution equals sigma divided by square root of n. This one is very important. If we see we have 95% confidence, that means in 95% of all these possible samples, it says possible. The reason is because we don't even need to do all these samples. We need only do one. But all these samples are possible. So in 95% of all these possible samples of the same size n, the mu will be indeed fall in our confidence interval of the 95%, in 95% of the confidence intervals. Only 5% of the samples would X bar, the mean of the sample, be further away from mu. So in this example here, look at this. The first X1 bar is here. So yes, this mu is within, see this one. This is X1 bar, and this is plus 2 standard deviation over square root of n. This is minus 2 standard deviation over n here. And this one is X1 bar plus minus. So this gives us the confidence interval from the first sample. So this is the confidence interval from the first sample. And if we check the real mu, yes, it indeed contains inside this first interval. How about the second one? The second one is here. The second x bar 2 is here. And plus minus 2 of this, it will give us the second interval from here to here. So that's the second interval. So that is C, confidence interval 2. And let's check the mu. The mu, yes, it is within this range. Because mu is here, right? It's within this range. How about the last one? The last one, the x bar 20 is here, and plus 2 standard deviation give us here, and minus 2 standard deviation give us here. So the confidence interval C20 is from here to here. Now look at the real population mean. It is here, which means it is here, so it's also inside this interval. Alright, there is an exception. Here, this one. This is 1, 2, 3, 4, 5. So this is CI5. CIX5 bar is here, then plus 2 standard deviation, minus 2 standard deviation, give us the interval from this point to this point. Now, let's check the real population mean. It is here, which means it is here. So it is outside of this confidence interval. We have 20 samples here. This is the only one that the interval does not contain the real population mean. So that is roughly 5%. 1 out of 20 equals 5%. If we do a lot of more, then we may have some other intervals that cannot contain the real population mean, but that is only 5%. So that is the meaning for 95% confidence. There will be a lot of confusing statement about this 95% confidence we are going to discuss or examine later time. But here, we mentioned this several times, the meaning of this 95% confidence interval. Okay, let's see how really how to understand this or other some confusing statement. Can we interpret a 95% confidence interval? 95% confidence interval as an interval with a 95% probability of containing a population mean. We have this 95% confidence interval. So confidence interval. Can I say this confidence interval has a probability of 95% that contains the population mean? Is this good or not? All right, let's check the first one. If repeated samples were taken and the 95% confidence intervals were computed from each sample, for each sample, 95% of these intervals, we means there are a lot of intervals, and 95% of them intervals, and 95% of them will contain the population. Is this good? Okay, so this statement we mentioned a lot of times. Yes, that is correct. Okay. We are given this 95%, C equals 95%. We are given this confidence interval. The correct interpretation is if we repeat samples a lot of times and with the same method. What method? Same method is this one is calculated from this plus minus 2 standard deviation from here. Right? if we repeat many more random samples, we use the same method here to calculate a lot of confidence intervals. For each sample, we have one confidence interval. We have a lot of samples. We said if we do a lot, then we are going to get a lot of confidence intervals. Then 95% of these confidence intervals will contain the real population mean. So that is a correct understanding. Okay, now look at the second one. A 95% confidence interval, this one, 95%, we have only one interval, confidence interval here, has a 95% probability of containing the population mean. So this one has a 95% probability contains the real population mean. Is this good or not? Actually, this is not correct. Because although we do not know the population mean, but it is a fixed number. Once we have this interval, that mu either inside this interval or outside this interval. If it's inside, that means it is 100% contains the population mean. If it's outside, that means it's 0%. There's no way we said 95% probability. This 95% probability is not the right way to interpret this 95% confidence. That is not the correct way. Right? The population mean either inside 100% or 0% outside. There's no way to say 95. Right? It is only a yes or no question. So this one is not correct. Okay, the next one, let's check this one. 95% of the population distribution is contained in the confidence interval. What does that mean? We have one confidence interval. It says 95% of the population distribution. Okay, the population distribution may look like this. Here, the population distribution may look like this. And the confidence interval is from here and to here. So this is the confidence interval from here to here. And it says 95% of the population distribution is contained in the confidence interval. Is this correct or not? Okay, we assume this one is correct. Right? So this one for confidence interval 1. Now, I will form the second confidence interval. As we already know from here, the second confidence interval may be different. It's definitely different than the first one, or maybe even very further away. Suppose the second one is, the interval is from here to here. That is possible, so that is CI2. And based on this interpretation, this one will contain the 95% of the population. So this one here will contain the 95% of the population. Because the population distribution is fixed, so it is this one. So there's no way for this interval to contain 95% of the population. So even if the first one is correct, then the next one will not be correct. That means this one here definitely not correct. This is not the right way to interpret it, the 95% confidence level. So I hope everybody can understand. The first one is the only way, is the only correct way to understand the confidence interval. This is important. We discussed the confidence interval. So how to write the confidence interval? So basically we have two ways to write the confidence interval. The first one is we use a mean plus minus m. The m is called the margin for error. The margin for error. So we are going to write mu is within the mean of the population. The mean of the sample. So this mean I need to specify here. This is the sample, the mean of the sample. Okay. So mu population. This one here is the sample. So the mu is within the sample mean plus minus a margin of error. And the margin of error, as we said, depends on some number times standard deviation, then divided by the square root of n, depends on here. So this one is a flexible number here. For example, so the interval is 120 plus minus 6. So that is the first method to write a confidence interval. The mean plus minus the margin of error. The second method is called two endpoint of an interval, because it is mean plus and minus mu. So the minimum is mean plus minus m. So the minimum is, the smaller one is the left hand side is mean minus m. The right hand side equals the mean plus m. So we are going to write x bar minus m to x bar plus m. So in this example, we are going to state the confidence interval is 120 minus 6, which equals 114, to 120 plus. So this is 120 minus 6, and this is 120 plus 6. So equals this, and this equals this. So either way works. So we can write this one 120 plus minus 6, or we can directly set 114 to 126. Confidence interval C, usually this is the percentage, indicates if we were to repeat the whole experiment n times under the same condition, we do the things exactly the same, then we would have n different confidence intervals. We said if we have the probability for us to have identical confidence intervals equal to 0. So we are going to have n different confidence intervals. The confidence level is the proportion of all these n confidence intervals that contains the true mean of the population. It represents the area and the normal curve within plus minus m of the center of the curve. So here, the confidence interval equals C means this is represented by C. And this proportion, or this probability equals C. And because the normal distribution is symmetric, so we know this area, or this area, equals 1 minus C divided by 2. Because this C plus something equals 1, plus this one times this one. So twice of this part equals 1. So this one will be equals 1 minus C, then divided by 2. So this one equals 1 minus c equals 2. So 1 minus c divided by 2. We are going to use these ideas later time. So here we just list this. This is very easy to understand. We already know this from chapter 1.